All right, so in the last video, we talked about how we identify whether or not a graph has an Euler path or an Euler circuit. And once we find one, then, or we know it exists, then how do we actually find it? How do we come up with the way to label it and make sure we're getting where we're supposed to be going? So this is what's called using Fleury's algorithm, okay? And it's really, like, he gets his name on it. He's the one that came up with it, but it's really nothing fancy. The basic ideas are the same, okay? If there aren't any odd vertices, so in other words, if they're all even, we know from before we can start anywhere we want to, okay? And if the graph has two odd vertices, we have to start at one and end at the other. So that step one there is not a shock. Then step two, number the edges as you trace through the graph, making sure you don't travel any edge twice. So you can number the edges. If you're going to number the edges, you can number them and then not necessarily write the vertices kind of bouncing back and forth between the graphs. Or if you prefer, you can trace the edge and just keep track of the vertices as you go. So like trace an edge and then write down the vertices as I've done in past examples. Okay, so it doesn't matter to me whether you actually number or whether you trace and just keep adding vertices in a list as you go. And then if you have a choice, make sure if you go across that next edge, you have a way to get back to where you came from, okay? So choose one that's not a bridge. In other words, if you go across it, that suddenly you're gonna be stuck and you can't find your way back from where you came from to part of the graph that hasn't been numbered, okay? So again, there is a lot of common sense in this one. So we're going to, first of all, use Euler's theorem to figure out if a path or circuit exists, and then find one if that's the case, okay? In these first two graphs, don't be alarmed that the circles aren't filled in. It's just the way the graph is drawn. Those are still vertices regardless, okay? So looking at this first graph, again, we need to look at the degree of the vertices. And I see right away that vertex E has odd degree, as does vertex D. So we have two odd vertices. Okay, D and E. And so this means that we must have an Euler path. Okay, an Euler path. So we need to begin at one of those odd vertices and end at the other. And there's not a right or a wrong choice as to which one you start and which one you finish in. They're both perfectly acceptable answers. I'm going to start at vertex E just because it looks like a great starting point, kind of sitting out there by itself. So I'm going to start at vertex E, and from E we would obviously have to go to C. Now, if you're just going to draw on the line and write C next, no problem, you don't have to number it. If you don't want to bounce back and forth and write every time, then just number, okay? Don't draw the line, just number it, vertex or edge number one. Then we need to go somewhere else, okay? You can go anywhere you want to go as long as you can get back to where it is you came from. So let's go up here from C, let's go to A. So either trace it and write down A or just label it 2, it doesn't matter. From A, we have to go somewhere again. So I'm gonna go, let's go to D. So we can go to D, or you can label that 3. From D, we have to travel somewhere, and there's nowhere I'm gonna go that I can't get out of. Whether I go to B or C, I can still escape. So let's go to B. That would be edge number 4. Then I obviously have to go back to A, so that would be edge number 5. Then from A, I have to get back out, so I could go to C, that's edge number 6. And then number 7, I end up back at D. And again, if you didn't keep track of those letters as you go, you would have to use your numbers on your graph to write them down. So you'd say, okay, from E, edge 1, I went to C. Edge 2, I went to A. Edge 3, I went to D. Edge 4, I went to B, and you can write down the path that you took in that manner. It's up to you. But please be aware that this is the Euler path, okay? You don't just leave a series of numbers on the page for, you know, the computer or your teacher or whoever to follow. You have to write down the vertices. All right, in this next example, is there an Euler path and Euler circuit? Neither one. And again, start looking at vertices and whether they have even or odd degree. So I'm picking out that one right there. That's got odd degree. One right below it has odd degree. The one to the right of it has odd degree. Golly, one to the left, like we've got lots with odd degree. If you keep finding them, you'll find that there's 8, okay? But our rule is if there's more than 2 with odd degree, there is not a path or a circuit of the Euler variety. Okay, so we have neither an Euler path nor an Euler circuit. So we can move on. Okay, pretty quick check there. We like those. We weren't looking forward to having to do that one anyway. Too many edges to concern ourselves with. And then we've seen this graph a few different times. We found out in the last one that vertex F and vertex D have odd degree. So 2 with odd degree. This must mean we have an Euler path. And again, we have to start at one odd degree vertex and end at the other. So again, it doesn't make any difference. I'm going to go ahead and start with vertex F. From F, again, you can travel wherever you want. I'm going to head up to B. That'll be number 1. And again, you can do one or the other. You can number or you can trace and write the letters. You eventually have to write the letters anyway. From B, we have no choice. We have to go over to C. That would be edge number 2. From C, you can, again, kind of take your pick. You can go to A, you can go to F, you can go to D. You can take the loop. Let's take the loop. I'm going to go around C. That would be edge 3. So from C, I list C again. Then I'm going to head over to A. That would be number 4. Then from A, we have no choice. We have to go over to D. That would be edge number 5. From D, I could go to C and I can still escape. I could go to E and I've got plenty of escapes if I go to E. So again, it makes no difference. Let's go to C. That'll be edge 6. Then from C, I have to go to F. I don't have a choice. That's edge 7. Then I have to go to E. Don't have a choice. That's edge 8. Then I can't go back to D yet because that would not let me go around that loop. So we got a loop next. That would be 9. So E back to itself. And then last but not least, edge 10, we go to vertex D. And again, that's not a unique path at all. There are plenty of them. So lots of potential right answers. All right, before we end this video, we're going to talk about this last little bit here. Okay, so this graph up here with the vertices not labeled, this one that I'm going to circle, that one right there, okay, that represents a housing development in Missoula, Montana. And the community requires that landscaping regulations be followed in terms of like the fencing you can have and how far from the road trees can be and whatever. So there's a lawn inspector. And her job is to walk down every street, making sure the homeowners are abiding by the regulations. And if they're not, they get fined. Okay, so based on what we figured out by saying there's not a path or a circuit, is it possible for the inspector to traverse or travel each street exactly once, ending at the same spot she started? Okay, so if you're going to travel each street exactly once, ending at the same spot she started, remember that that is an Euler circuit. Okay, that's what that's describing. And we said that no, there is no Euler circuit or Euler path for that matter. So this can't happen. All right. So the question is, she can't do that. She can't walk up and down every street once. So how is it that she can be as efficient as possible, minimizing the amount of backtracking or walking the exact same street twice? Okay, how can she minimize how many times she has to duplicate a street? And that's what the next video is going to work on.